So up next we have Bolun Chen, who is a Ph.D. student in theoretical physics. He earned his bachelor's and master's degrees from Beijing Normal University in China before he entered the Ph.D. program in the physics department here at BC in 2011. Bolun has broad interest in collective behaviors and spontaneous ordering in nature and has published 6 papers in peer-reviewed journals, receiving more than 60 citations. What the heck am I doing with my life? His current research focuses on dynamics of coupled oscillator networks and applications in neuroscience. Please help me welcome Bolun to the stage.
Thank you, thank you. Thank you for coming. Oops. Okay. So let's start. So this is a photo of the Great Smoky Mountains National Park in Tennessee. Every first week during the summertime, tens of thousands of visitors will pull into the park, drive to a small campsite named Alkmont. After sunset, people would walk into the woods, turn off their cell phones, and wait. Wait to see the most spectacular light show in nature. And that's the synchronous flashing of fireflies. So this is a time-lapse recording. So after it gets dark, you can see all the fireflies start to blink on and off while they're flying around the bushes. And let's just, if we focus the camera and zoom in a small region, you can see how this synchronous pattern is emerging. Fireflies congregate into small clusters, and in the dark forests, they fly around like little lanterns. And now you imagine that you are surrounded by hundreds of thousands of these fireflies, all flashing quietly in unison, from the top of the trees to the bottom of your feet. I was there last summer, and it was truly a once-in-a-lifetime experience. People were amazed by this phenomenon where a group of mindless insects act in such a highly ordered manner, like musicians in an orchestra, but without any training or a conductor. How could this be possible? How could this, after all, happen? That's a good question, and it puzzled scientists for over 300 years. The first key to answering this question came in quite late, and people just realized, okay, this is a very simple fact. Fireflies flash not only in unison, but also periodically. Let's think about the clock. So we can start at 12 o'clock, and the hour hand will rotate uniformly around the disk. And after some time, it goes back to the starting point. So periodicity means something that repeats. We can visualize the lightning process of the firefly as an internal clock. Let's assume at 12 o'clock, our little bug just emits a burst of light. It needs some time to recover and charge the battery before it's able to fire again. But unfortunately, this internal clock is quite sloppy. Right? So this is a good clock, like the watch. If I see the hour hand points to 3, I know it's 3 o'clock. If it's points to 6, I know it's 6 o'clock. In other words, if I plot the clock time versus the actual time, all the points should fall onto a straight line. Perfect. However, the internal clock of the firefly is just the opposite. It runs very fast at the beginning, gradually slowing down. Then it becomes extremely slow before reaching 12. This curve is called a charging curve. Each point on this curve represents an eternal state of this little bug. Let's assume this little bug starts at 0. It incrementally gathers its potential and shines when the curve reaches 12. But remember, on the clock, 12 is the same as 0. So the firefly starts to charge again. And this whole process repeats. Now we can ask, what happens if we put two fireflies together? It turns out one firefly's flash would affect the other one. Here we have two fireflies represented as two clocks. You can see the left black one is pretty close to the threshold, while the white one still has a long way to go. First, the black one emits a burst of light, and the light will push the white one to speed up. So it jumps directly from 9 o'clock to 12 o'clock. Now it reaches the threshold, so it fires. This is how these two fireflies are synchronized. Once they're locked, they will be moving together, hand in hand, and never lose the sync. The same argument also applies for any number of fireflies. In this computer simulation of 50 fireflies, everyone is receiving light signals from its neighbors and will emit a light pulse if its internal clock reaches the threshold. You can see gradually more and more fireflies are joining together into a larger cluster until suddenly all of them are firing in the same pace. Okay. In a more rigorous way, my advisor, Randy Marollo, and his collaborator, Steve Strogatz, proved that for such a system, synchrony is always stable. What we have discussed are two key elements in their proof. All fireflies are following the same nonlinear charging curve, and they are coupled through sudden pauses. If both conditions are satisfied, sync is inevitable. Their proof solved a long-standing problem in a convincing and elegant way. Moreover, this model is a general framework for understanding a wide range of problems, such as neuroscience. There are about 100 billion neurons in the brain. Each one of them is connected to another 10,000 neurons. So the total number of connections in our brain is much, much larger than the total number of stars in our galaxy. The dynamic of this immense network determines how we feel, what we think, and who we are. Trying to understand this complicated system seems very intimidating. However, if we just focus on one neuron, its behavior is pretty simple. And actually, to a large extent, the cell evolves in a similar way as a firefly. Its voltage, membrane voltage, increases following a bending nonlinear curve. And when the curve reaches some threshold, the neuron will emit a burst of electric pulse to other neurons. Remember that if we have a bending curve and a pulse, there must be synchrony. But what's the sync in the brain? It's called the brain waves, which are collective electrical ripples under the scalp. Remember those lie detector tests in crime movies where a guy just wear a head full of electrodes? Those electrodes are reading brain waves. So now we can use the same mathematical equation for fireflies to describe our brain's activity. Here is a simulation of 2,000 neurons. In the left panel, when we turn off the pulse coupling between neurons, their general firing pattern are quite noisy and random. But once we allow neurons to communicate each other using their pulses, they synchronize themselves very rapidly in terms of those clear vertical stripes in the lower panel. And if we measure the electric currents, we'll see a bunch of sharp spikes in the upper panel, and they are the brain waves. In the past few years, I've been working closely with Professor Engelbrecht, who is sitting in the audience, and Rennie on this front, combining ideas from physics, mathematics, and neuroscience. We're trying to extend this powerful way of thinking and mathematical framework to adopt more general cases. Because instead of fireflies and neurons, there are many different types of sync in nature. For example, the jet lags. Our sleeping cycles are coupled or locked to the 24-hour day and night period of the Earth. So when we travel across multiple time zones in a day, the internal rhythm are disturbed, and that causes sleeping problems. Also, many female college students found their menstrual periods tend to synchronize with their roommates, which is another interesting case for mutual synchrony. In sum, synchronization is a universal phenomenon in nature that brings order out of chaos, and we can understand its mechanism using simple and elegant mathematics. And also, I want to show you one more slide about another kind of sync that is induced by some external driving force. All right, before the end of the talk, would you like to see a live demonstration of synchrony? Yeah. OK, then clap for me. Stop, don't stop until we synchronize. All right, thank you very much. I hope you enjoyed the talk. Thank you.